Okay, students, let's do this projectile problem where we've got a projectile that's launched at an angle. This one's a little weird, right? A little gross. It's from your book. We've got a flea that's jumping, right? And so the flea jumps with an initial speed of 2.2 meters per second. And then it does that. It leaps at an angle of 21 degrees with respect to the ground, with respect to the horizontal. And for this problem, it says that the flea is in the air for 0.16 seconds, and we want to find out two things. We want to find out how far does it go horizontally, the range, right, delta x, and we also want to find out what is the height that it actually jumps. Okay, so I've just drawn in my coordinate system here. I've got my x and my y axis, and I'm just going to draw in a path that shows, there we go, the path that shows the flight of the flea. This does not have to be drawn to scale. In fact, mine will never really be drawn to scale because it's just kind of difficult to do that. So this right here, this would be our velocity. And so that would be v equals, for this case, 2.2 meters per second. And then this angle is obviously way off from what's actually measured, 21 degrees, but it's just easier to fit it in the diagram. And so what we need to do then is, because this is launched at an angle, we need to resolve it into its components. So this side here, this is Vx, and then this side over here, this is Vy initial. And what we can do is we can use some of the tricks that we've used before, because what happens is, let's say that this is right at y max. So this would be the highest point, right, this dot right here, that the flea goes. That's halfway through the path. So some of the tricks that we know about this is that we're halfway through the total range, right? Delta x divided by 2. We're also half of the total time that we're in the air. And we know at this point our y velocity is 0. So sometimes these tricks can help us. So let's continue listing everything that we need and also what we want to find. So it says that we want to find out, number one is how high does it go? And we also want to find out how far does it travel? What is the range? The other thing that we have for this problem is, in this case, it actually gave us the time interval, right? So we do have what delta t is equal to. This would be 1.6 seconds. That's the total time that it takes for this thing to jump from over here on the ground and then land back on the ground over here. Now remember, we can split this parabola right in two when we land at the same height that we were jumping or launched from. That's the only case where we can do these tricks that happened at y max. All right, let's make our table so we can see what we've got. We'll make our x and y table right here. So we actually have Vx because we have our initial velocity and we have our angle. We don't have delta x, and we do have the time. We have that 1.6 seconds. So that's good. We have 2 out of the 3 variables in the x direction. In the y direction, we've got Vy initial because we have our initial speed. I'm just going to write this as Vi over here. And we also have our angle. We always have gravity's acceleration. For this problem, we do have the time. And we also can write that Vy is 0 at y max. So this might give us another data point if we need it. And then, oops, sorry, that's wrong. We want to find out what delta y is equal to. Okay, so we can do this in a couple different ways. We've got a few different steps that we can do. And it doesn't matter the order that we do this in, but let's just look at step number 1, right? If we want to find the height, delta y, what we can do is we can use Vy equals 0 at y max, because what will happen is that Vy equals 0 will become our final height, our final speed to get that height. And then the other thing that we need to do for this one is we need to find delta x. So to find our delta x, all we need to do is use our one equation, right? Use delta t, and we can use our Vx. All right, so now we have a plan for this. Let's do the first step. We'll just do this one over here. So what we want to do then is we need to find an equation that has the variables that fit over here in order to find our final height. So the one that I'm going to use for this one, and we actually have choices because we have so many things for this one, but just to show you how to use the trick for y max, we've got Vy final squared equals Vy initial squared minus 2g times delta y. And since we're launched at an angle, we know that Vy initial equals Vi sine theta. So we can do a couple things. We can do a little substitution here, and we can put that in. And the other thing that we can do is we know that at Vy final, if we go to y max, that the final velocity is 0. This would actually go away. So if we rewrite this, we have 0 for our final velocity at y max. This part here becomes, with our substitution, Vi squared sine squared theta minus 2g times delta y. And then all we need to do from here is just a little bit of algebra to rearrange this. Delta y equals Vi squared sine squared theta divided by 2g. So this equation will solve to find what our height is supposed to be equal to. So if we put the numbers in for this, we have our 2.2 meters per second squared. We've got sine of 21 degrees, and you can write this a couple different ways. I'm just going to write it like this, squared, divided by 2 times our 9.81 meters per second squared. And this will give us a height of 0.032 meters, which really is 3.2 centimeters. And you can choose how you write that answer for this one. So that's the height. For the second part, part number 2, is we want to find what our delta x is equal to. Well, we've got Vx equals delta x over delta t. And remember, there are no kinematics for this, no acceleration in our x direction. If I rewrite this for delta x, it's just Vx times delta t. Now, just like with our y direction, because we are launched at an angle, Vx equals Vi times the cosine of theta. So I need to do another substitution. I'll take this and I'll put that in for Vx over here. So we have delta x equals Vi cosine theta times delta t. So here's our equation that solves for the range. How far does this thing actually jump? So delta x equals, we'll put in our 2.2 meters per second times the cosine of our 21 degrees, and the time of flight is 1.6 seconds. The calculator does most of the work for us, and we get 0.33 meters, or to be consistent with what we did over there, this would be 33 centimeters. So there's not one way of doing projectile problems that are launched at an angle. We'll still follow the same procedure. We'll draw the diagram, right? We'll set up our table, and then it's always a good idea to kind of come up with a plan to see what you can use from your diagram and your table to solve for your unknowns. I will see you in class.